So the next speaker is Piyush Kumar Sharma from KU Leuven, and he's going to talk about latency-aware routing in mixed networks.
Yeah. Hello all. So my name is Piyush Kumar Sharma, and I'll be presenting this work, LARMix, latency-aware routing in mixed networks, which was done in collaboration with Mehdi and Claudia at KU Leuven. So let's get started. What exactly are mixnets? So they are a type of anonymous communication network similar to Tor. And how they provide anonymity is by routing traffic through multiple hops, which makes it difficult for a local observer to de-anonymize the traffic. And at the same time, it introduces some notion of mixing. That is, it tries to introduce some delay or some kind of overhead, so that if an adversary is analyzing the network, they will not be able to trivially correlate the traffic. And based on the kind of mixing that these mixnets does, there are multiple types. And recently we have seen deployments of a type of mixnet in the NIM network, which has a layered topology, and it does something known as Poisson mixing. And what does this mixnet and this kind of a mixing look like? We can understand with this diagram, where we assume that there are a set of users who are trying to access a set of destinations. And all of this traffic will be routed through this mixnet, where you can see that there are multiple layers, in this case 3. And each layer consists of a few nodes. So whenever a client transfers the traffic, it has to go from one of the nodes in layer 1, then to one of the nodes in layer 2, and then layer 3, and eventually the destination. Apart from the propagation, in each mix node itself, they do some sort of mixing, like delaying packets randomly, so that the mapping between the incoming and outgoing packets is not trivial to detect. So what is the issue? Given the mixnets provides stronger anonymity guarantees, in turn, they incur a lot of high latency to the end-to-end flows. And this limits the kind of applications that can be supported over these mixnets. So a simple question we asked is, can we somehow reduce this latency in layered mixnets so that we can support a wider range of applications? And what kind of impact can it have on the default anonymity properties that such a mixnet provides? In order to answer this question, we need to know what are the different sources of latency within a mixnet. So the first source of latency is what we call the mixing latency, which happens at each mix node. So if you look at this, the box on the right, so this is inside a mix node where there are multiple packets. And you can see that D1, D2, D3, these are the corresponding delays that these packets have to stay in this mix node before leaving it. And maybe if these mix nodes even came in the order of D1 to D6, but maybe the packet which is leaving first would be D3 because this delay is random, right? So this kind of mixing, as you can imagine, the more the random delay we add, the more number of packets the other packets will get mixed to, and then it will make detection difficult. So in turn, providing anonymity. So this mixing has a direct relation to anonymity. But apart from this latency, we have another source of latency, which we call the propagation latency. That is, once we have decided on a route, it has to transfer from a mix node to the next and then to the next. So this is what we call the propagation latency. It does not directly impact anonymity, but because in the default case, everything is random, that a node from layer 1 can transfer to any node in the layer 2. So that randomness provides some kind of anonymity, but not directly. Great. So given these types of latency, which latency is this work targeting to minimize? So this is the propagation latency. And even in the end-to-end propagation latency path, we are only interested in minimizing the latency introduced by the mixnet. So this brings us to the actual design goals, which is, as you have guessed by now, to minimize propagation latency within layered mixnets, while also minimizing its impact on anonymity. And rather than going all in and saying this is the best approach, we try to provide a tunable parameter which controls this latency anonymity trade-off in the design, where a value of 0 means that the path is completely fixed. A node in layer 1 receiving a packet will always transfer its packets to a fixed node in layer 2. And the value of 1 means uniform routing. That is, with equal probability, a packet will be forwarded from one layer to the other layer. And on top of that, we want to ensure that this kind of biased routing should not lead to some kind of imbalance in the network, that is, some nodes are receiving large amount of traffic and some are getting underloaded. So how do we do that? So there are multiple approaches we develop for different stages of the mixnet. So as you see, I showed you a diagram of a mixnet which already has these nodes arranged in different layers. So by default, it's done randomly, that we have a set of mix nodes and they are randomly assigned to these layers. But in the step one, what we try to do is we try to devise an arrangement strategy such that it aids us in selecting low latency paths with the help of a routing policy. And once we have this arrangement ready, we can actually, in the next step, actually build the routing policy which can exploit and, based on the tunable parameter we provide, make it faster or slower. And once all this has been done, we need to ensure that the load is balanced. So now we'll look at these steps in a bit more detail. So the first step, that is the arrangement of mixnets, is in turn divided into two steps. So we have a bunch of mix nodes, and then we cluster those mix nodes based on location proximity. So our nodes within a cluster would have very low latency within that cluster. And once we have these clusters, we use them to diversify them in different layers. So let's just try to quickly look at how this look like visually. So let's say these are the set of mix nodes that we have available. And this is how, let's say, the clustering, for example, happens. So you can see that there are 3 clusters, the green lines, blue lines, and the orange ones, and they are based on location. Now let's say we have to construct a mixnet. That is where our diversification algorithm of arranging will come into play, where let's say we have 3 layers, and in each layer we wanted 3 nodes. So you can see that the nodes are diversified, that each layer contains 1 node from each cluster. So in this case, if I want to have a very fast routing policy, I can ensure that all the packets that are coming to the orange mix node, they go towards the orange mix node in the second layer, and subsequently the orange mix node in the third layer. And since they are a part of a single cluster, the latency will be minimized. So this is how we kind of create the mixnet as a first step. And once we have this mixnet, we now want to basically define what will be the routing policy, like how exactly will you be transferring these packets. And this is kind of the magic formula we use to do that. I'll not go into the exact nitty-gritty details, but I'll give you an intuition of what this formula is basically telling us. So if you look on the left side, you'll see that there is a probability where, given we have selected 1 mix node in the first layer, what is the probability of selecting any other mix node in the second layer? By default, it's all equal. If there are 10 nodes, it's 1 by 10 of transferring to each packets. But we want them to be more biased towards lower latency paths. So that is where, if you'll see in the numerator, there is a component Lij, which is the latency between 2 nodes. We take that as a factor, and it is in the denominator because a lower value of latency would be in the higher component. That means higher probability weight, and conversely. We multiply that with some factor, which here is 1 by E, because we want to control how much of the latency we want to accommodate while deriving the probabilities. And on top of that, because we had this parameter tau, which controls how much you want to bias it towards latency. So both of these factors are raised to some function of tau, which basically ensures, as I said, if a value is 0, it will be very deterministic, and 1 will be the default random case, and all the values in between will give some latency anonymity trade-offs. Great. And the last step is, once we have the mixnet and the routing policy, we want to ensure that there is no node which is receiving an unprecedented amount of traffic. So there's a simple way we detect which nodes are receiving. If, let's say, in the first layer, each mix node is receiving 1 unit of traffic, then all the mix nodes in the layer 2 should also be receiving exactly 1 unit of traffic. That is what we mean by balancing the load. So we create this, we calculate this overloaded mix nodes, and then we have 2 approaches of redistributing those overloaded mix nodes traffic to the other underloaded mix nodes. And we do that by greedy balancing, which is we kind of still keep the latency bias in mind when we are redistributing those probabilities. And that is why this process is iterative, because we have a set of overloaded, underloaded nodes. We take it, we redistribute them. There might still be overloaded nodes, and this process repeats. Naive balancing is simple. We just calculate what is the overload, and we proportionally distribute them among the remaining nodes. And this is a one-shot process, and this is very easy to implement. So this was all about the approach. And this is how you can actually get a sense of how the routing and balancing works in conjunction. So, okay, never mind. So as you can see here, there are clients, there are 3 layers, and there are these 3 mix nodes. So each layer is receiving equal number of packets, that is 3, which basically kind of ensures that there is load balance. But what you will see here is, let's say we analyze the first blue node in the layer 1. It has 2 outgoing arrows, one to the green node and one to the another blue node. But it is sending 2 packets to the blue node and 1 packet to the green node, and no packets to the orange node. So this is the case where we are having some latency trade-off, where faster paths are preferred. But since not all the paths are considered here, so there will be some reduction in anonymity as well. So the default case of 1 would mean that there will be 3 arrows from the blue node, and each of the packet will be going to the orange, green, and blue node, and so on. So this brings us to the evaluation. And for evaluating this approach, we, as you can imagine, needed a set of basically mix nodes, which each have some latency data to each other in the network. And for that, we use the RIPE Atlas nodes, anchor nodes measurement data. And this is what the distribution of the nodes considered for the evaluation looks like. And once we have these data sets, we performed 2 sets of evaluation. Since our contribution was mostly in reducing the latency, overhead during the routing period, and we do not touch the mixing latency. So we devised a novel approach which exclusively tells us how much benefit we got in terms of anonymity or latency due to routing. And the simulation, that is the second set of evaluation, basically gives the overall picture that with your reduction in routing and what we already have for mixing latency, what is the overall scenario looks like. And we measure 2 basic metrics for latency and the anonymity. And anonymity we measured in terms of entropy. And with these things, these are the experiments. This is the overview of experiments that we performed for evaluating LARMix, where you can see that there are 3 classes of experiments that we performed. And each class had certain variables and certain entities that we were measuring for the performance and anonymity. So if we take an example, let's say, for evaluating our latency-aware routing scheme, we had different components of arrangement in terms of random arrangement, the diversified arrangement that we developed, and I showed just a few slides back, and a worst-case scenario. For routing, we vary the value of tau from 0 to 1. And for balancing, we consider what is the scenario when no balancing was considered, what is the scenario when we considered the 2 greedy and naive balancing approaches. So in the interest of time, I'll be just talking about 2 of the results of all the combination. And so this is what the first result looks like, where if you look at the diagram on the left, it basically has, on the x-axis, varies the randomness or the biasness that we want to have towards faster routes. So tau equal to 1 basically means the default case, that is random routing, and there's no optimization at all. And 0 means that there is full optimization that we can do from our approach in routing. And these different arrows basically signify different types of balancing. The green arrow means we have not done any balancing at all. And in that case, you can see that the entropy goes very low for that. And the other arrows, the red and the blue one, they basically correspond to the greedy and naive balance. And correspondingly on the right, we have the latency for the same bias values. And as you can see that for low latency, when we do not incur any imbalance at all, the reduction is almost 8 times from what you will get by default in a mixnet. But a more realistic estimate for a value of 0.6 with greedy balancing approach, we get a reduction of 3.5 times in latency and with a loss of just 0.8 bits in entropy. Another interesting result that I would like to talk about is given a latency constraint, that is, if a network designer wants that the mixnet should not give more than, let's say, 200 milliseconds of latency, what should be the division among the mixing latency and the propagation delay in the network, such that we have maximize, or we basically obtain the maximum anonymity. So in this case, we performed a simple experiment. We varied the value of tau. For each value of tau, we basically measured what is the propagation latency. So if we look at the value of 0, the propagation latency came out to be 68 milliseconds. And whatever is the leftover out of 200, that is about 132 milliseconds, we distributed it as the mixing latency for all the nodes. And then we measured for this configuration what will be the entropy. And as you can see that the best case we observed was when the value of tau was 0.7. And this is a slightly surprising result because, as I said, by default, the maximum mixing latency should have given us the maximum anonymity, but it is not the case here. As you can see that the mixing latency is 35 milliseconds for the best case, but it could have been as high as 44 milliseconds. So when we have these tighter, lower latency constraints, then both the mixing latency as well as the propagation latency need to find a sweet spot in order to maximize anonymity. And so this was about all the performance, and we also did a security analysis where we considered different sets of adversaries, and basically measured the fraction of corrupted paths, which is how many nodes, which is basically if all the nodes in a path are adversary controlled, that they can trace end to end who is the originator of the packet. And this is what the result looked like for one of the evaluation, where you can see that the worst case is kind of the upper bound, which is introduced because of our evaluation. And although it seems very high, it's theoretically high, it's practically very difficult to reach this conclusion. And the practical strategy, that is, let's say an adversary has all the mixed nodes in a single location, and since they're in single location, they might be part of one cluster, and the diversification algorithm would distribute them in different layers. So that gives slight advantage on top of the random one, but still the advantage is not very high. And so to conclude, so this work looked at basically reducing the latency in mixnets so that wider range of applications can be supported on top of it. And while reducing latency, we tried to keep in mind to have as less impact on the anonymity as possible, all the while trying to balance the load in the network. We performed extensive evaluations to demonstrate the practicality of the design. And the implementation code is public, where it received all the 3 badges for availability, functionality, and reproducibility. You can scan this QR code if you'd like to have a look at the code or would want to build on top of it. Thank you.
So first I have a quick question about the practical implication of what you did. So for example, you use the RIPE network, but that doesn't seem necessarily super practical. Did you look at other kind of node deployments? For example, take the Tor current deployment, right? And see what kind of privacy and latency can you get, like the maximum wise for that particular setup? Have you looked at something like that?
Yeah, so thank you so much for the question. So the ideal scenario would be if we test it in an actual deployed mixnet, because those latency and the guarantees that we would capture would be the most realistic. So at the time of when we were doing this research, we did not have access to this data, but post that we have had access to data, and the kind of reductions that we see from RIPE Atlas data, we see similar reductions in the data that we use from the NIM mixnet that is already deployed. So we did consider different data sets for evaluation.
So Alexandra Dmitrienko, University of Würzburg in Germany. My question is, do you think that inflation bandwidth style attacks, which are possible in Tor, could be also applicable here if the node, for example, tries to lie about its latency?
Yes, they, I think, would be applicable if we do not have the load balancing in place. Because if you look at maybe in detail, even in the paper, all the nodes that are in the network, they receive equal amount of traffic despite being biased towards faster routes. So without having that factor where you can, you have this opportunity of maybe increasing the traffic on one particular mix node, I think they would be difficult. But I cannot be like 100% certain that, okay, it's totally, robust to bandwidth inflation attacks.
Okay, thank you.
Any other questions? Okay, so in that case, let's conclude the session. Lunch is waiting, and we can talk more offline. Thank you very much.